Hello, welcome back. Okay, did we do this problem now? Well, hopefully you did. When you're doing this, you draw out all of your structures, right? Remember that if there's a coefficient, that means that there are two of them in this case, and so you have to draw both of them. They're both part of the reaction. So those are the bonds that you're breaking. Those are the bonds that you end up making, and you should end up with negative 1,194. Okay, so hopefully you got that. That's what I got, so hopefully I didn't screw up either. All right, next. Representation of enthalpy. So we know enthalpy is just heat. You can have a lot of different representations of it. So you can have heat of reaction, heat of formation, heat of combustion. They're all still enthalpy. It's all change in heat. It's just that in one case, it's representing a general reaction. In another case, it's the heat of formation. So it's like forming a substance from its individual elements, like a synthesis reaction. And then heat of combustion, which would be just the heat in a combustion reaction. So they all represent your heat change, basically. It's just specific to like specific reactions, okay? It's very similar to your equilibrium constant. Remember in Unit 3 how your K value, it could be Kc, Kp, Ka, Kb, Kw. It was always the equilibrium constant. It's just Kc is in terms of concentration, Kp was in terms of pressure, Ka was for an acid, Kb was for a base, and so on. But it was always your equilibrium constant. You can find your delta H using this equation. So if you wanted to sum up your heats of formation of your products and then subtract your heats of formation of your reactants, that would give you your delta H. And this equation is given to you on your equation sheet. The enthalpy of formation for any pure element is 0. So like the amount of heat it takes to make hydrogen is just 0 because hydrogen exists, okay? But it exists as H2. So if we wanted to find like just a single H, or like if it existed H4, then that wouldn't be 0 because that's not its standard state. When you're doing your online homework, you might need to look up some values, and when you're doing your book work tomorrow, you're going to need to look up, you might need to look up some values, but you will never need to memorize them, okay? And on a test, I would give them to you, and College Board will give those to you. All right, so for example, let's go ahead and do this problem. You've got 2NO and O2 making 2NO2. So here's a little chart with some information for you. You need to find the delta H for this reaction. So go ahead and pause this video until you have solved it. Okay, did we solve it? If you did, you should have gotten negative 113 kilojoules. Remember that the reason why they did not give you any O2 is because O2 is just oxygen. That's a pure element in its natural state, right? So that's just going to be 0, okay? But that's really all you have to do for these types of problems. All right, so endo and exothermic. In an exothermic reaction, energy is exiting. So it's going from the system to the surroundings, and the system is going to feel hotter. I really should change this. Rather than the system gets hotter, cross that out and say feels hotter, okay? Because it's going to feel hotter to you because it's releasing energy and it's giving you the energy, okay? Endothermic means energy is entering the system, so it's going to feel colder. So please change that on your note-taking guide. The system feels colder because it's taking away your heat. So it's absorbing your heat and putting it into the system, okay? When you are trying to figure out whether something is exo or endothermic, my weirdest piece of advice to you is to think of yourself as the thermometer. Know that you and the thermometer are part of the surroundings, right? So if the thermometer is getting hotter, that means energy is being given to the thermometer. Well, if it's being given to the surroundings, then the system must be losing that heat, which would be exothermic. Okay, so just put yourself in the shoes of the thermometer. All right, so graphically, if we were to show this, right, let's say we start off with carbon and oxygen, and then we end up down there with CO2. That would be an exothermic reaction, right? So your change, that would be your delta H, and it would be negative. When you write it in a chemical formula, you would make that heat a product, okay? So the heat is just going to be the product. When you have the opposite going on, okay, you're going to start down here and you're going to end up way up here. Now you're going to have a positive change in energy. So that energy value is going to become part of the reactants because you're putting energy into the system, okay? So here's another example. So this would be a combustion reaction, right? This plus oxygen making carbon dioxide and water. Here, your delta H is negative because your heat is a product, okay? Now, if you were to flip that reaction, now your delta H is positive. So your opposite reaction, whenever you're doing a reverse reaction, you're flipping the sign of your delta H, okay? And in this case, now it would become endothermic. All right, so let's say I've got this chemical reaction. Okay, so this is the same one as before. First of all, is this reaction exo or endothermic? Yes, good job. You said exothermic. I knew it. Now, if you've got 10.3 grams of CH4 and you burn them, how much heat is going to be produced? So you're starting off with 10.3 grams of CH4, right? You're trying to figure out how much heat is going to be produced. Well, looking at this equation, we know that for every 1 mole of CH4 that's burned, we will get 802.2 kilojoules of heat back. Our problem is we don't have 1 mole. We have 10.3 grams. So what do we have to do? Convert it to moles. So you're going to start off with 10.3 grams. You're going to set up your first conversion. I messed up on the animation on this. Sorry. Okay, you're going to have 16.05 grams down there. That's your molar mass. And up top, you'll have 1 mole of CH4. So there's your first conversion. Now we've converted it into moles. Now, it's like setting up a mole ratio. You know that for every 1 mole of CH4, you're getting 802.2 kilojoules back. And so, you would end up with 514 kilojoules for every 10.3 grams of CH4 that you've burned. Okay. Now, let's say, for example, that we were using O2 instead. That mole ratio is 2 to 802. So you would say 802.2 over 2 moles of O2. Okay? So it's a normal mole ratio. It's just you're using a heat value. All right. Now when you're dealing with phase changes, you need to think now of the motion of the molecules. Okay? You know that solids just kind of vibrate in place, liquids move around a little more, and gases are just crazy. Okay? So think about whether energy is being released or absorbed. So for example, if you're going from a liquid to a solid, okay, you're freezing water. You had a liquid with a moderate amount of energy, and now you're at a solid that doesn't have as much. You lost energy. So that would have to be exothermic because energy was lost. Okay? If you're going backwards the other way, let's say we're going from liquid up to a gas. Okay? So you're heating it up. These molecules are now moving faster. They are absorbing that energy, and it's endothermic. Okay? So even though going from a liquid to a gas, you do have to heat the substance. This stuff is going to be getting hotter, but it's the surroundings that has to heat it up, right? When you put water on a stove, you're heating it up to boil it, but like the surroundings were providing the heat, okay? So they're absorbing that energy to turn into a gas. So whenever you're dealing with just phase changes, just think of the motion, okay? Whether it's a solid, liquid, or gas and how fast they're moving. All right, so let's do this example. I have water at 25 degrees Celsius. I'm dissolving ammonium acetate in the water, and I find that the temperature decreases to 15 degrees Celsius. Is the heat transferring from the solution to the surroundings or from the surroundings to the solution? Think about it. Okay, did we think? So here's what's happening. If our solution is going from 25 down to 15, what did I tell you to think of? You're thinking of the thermometer. Put yourself in the shoes of the thermometer. The thermometer is getting colder, which means energy is being taken away from the thermometer. The thermometer is part of the surroundings. So it's being transferred from the surroundings to the solution. Okay, so would that process be exo or endothermic? It would have to be endothermic, going from the surroundings to the solution. So the solution is absorbing that energy from the thermometer. Okay? Make sure on your note-taking guide that you are actually explaining this. So if you need to go back and rewind this and listen to that explanation again, then do it. All right, last one. You place a pot of water at 25 degrees Celsius on the stove and you heat it to 100 degrees Celsius when it starts to boil. Is that process endo or exothermic, and why? Think about it. That is also going to be endothermic. So now, yes, the temperature is increasing, but you're not doing a chemical reaction or anything. You are putting this on the stove. The stove is giving the energy to the pot of water. So this is going, again, from the surroundings to the solution. Okay? So the water is absorbing that heat. So that is going to be endothermic. Okay? All right, that is the end of your notes. Please make sure you've filled everything in. Tomorrow you need to bring your textbook because you are going to have some bookwork to complete for this, and that assignment will be posted on Google Classroom tomorrow. Have a wonderful rest of your day, and I can't wait to see you when I get back. Bye.